what's fun about that is we can just duplicate this here, and this is going to stand in for the geometry that we're getting rid of. And all we need to do is delete this. So now we have the same thing, same effect. And so we've got the geometry that we're getting rid of, basically, and we have the leading edge where we're going to source all of our simulation effects from. If that all makes sense. And last of all, you can see we're modifying p-scale, but really we want to get rid of all the points that we don't need. And that's where this next line comes in. We're saying if the p-scale value is below a certain threshold, in this case 0, 0, 1, remove that point. And then that should give us this. So sourcing. Yeah, anything on that so far? Any questions?
So the width represents the leading edge?
Yeah, the width is this ramp right here. So you can see this, we're normalizing the age, getting a value from 0 to 1, and then mapping that to this ramp. Then we're dividing it by the width. That just can make this ramp, it just makes it thinner. So you can see here, I can actually, somebody was asking about how to control what's happening at the leading edge. This would be the way to do it.
Right.
So you can move this around. In fact, I think I'm using more interpolated nodes on the ramp in the actual effect, but keeping this at 0.5. Does that answer?
Yes.
Yeah.
Awesome.
So, and what I'm doing in the main effect here, you can see this is getting rid of what we don't need. Let's jump back into this real quick because you can see this more in practice. You can see this same expressions. Oh, I better be careful. Again, getting rid of making sure it's not a ramp that gets rid of things behind the growth. So it's just keeping everything. And then we've got VDB from particles here. This right here gives us our growth. And then we can just VDB combine that to get rid of the parts of the glass we don't need. So object merging in a VDB of our martini glass and then using a VDB combine set to subtract. So those points then subtract from the glass, and that gives us the dissolving away of our glass. All good? But in this case, in this explainer right here, I'm going to just keep these points just to keep things simple. All right. And next, we're going to just do kind of run through how we're going to source things for that effect and how we're going to use this to source things downstream into our sims. And we can start by just using a PopNet. How are we doing on time, by the way?
Don't worry about time. You just do your whole class, and if
Okay.
people have to go, they go. It's okay.
Okay. All right. Well, let's go ahead and set up a pop sim for this. Let's do. We're going to source. We're not going to scatter on surfaces. We're just going to take points, and maybe less. Let's do 1,200 points. We're going to source, and we run that. Actually, let's visualize. We just get kind of, random motion. We can actually, it's sourcing in the velocity. If we look at this, you can see velocity trails in the general direction of travel here. It's almost like they have curl noise, and that's because since they're finding the neighboring points weighted by that noise, they get this semi-random pattern, which actually works for us in this case. So, but what we really want is we want the particles to be taking velocity in the opposite direction, which is pretty easy to do. We can go here and in our attributes, particles by default inherit all the attributes from the points they're being sourced from. And let's just say minus 0.5. So cut it in half and push them in the opposite direction from the growth. And then actually, let's turn off this guide. And then you can see they're pushing up in the opposite direction. And let's go ahead and merge these. So you can begin to see how this effect is being built in kind of very basic, in a basic state. So there we are. We just kind of have them dissolving away. The particles are sourcing from this leading edge of our growth solve. And then this is demonstrating how it's getting rid of the geometry we no longer need. So now we talked earlier on that a very critical component for this whole process, this effect, is going to be advection. And we'll kind of illustrate that real quick here too. We might as well.
Before you move on, can I ask one quick question?
Absolutely.
Could we see the pop settings real quick?
Sure. Everything is set to default.
Default. Okay.
Yeah, I'm actually not doing anything in particular with the pop net yet, other than I'm saying we want to source from points, so we can set a constant birth rate, and setting the constant birth rate to 1200, so it's not not too many. In fact, we can turn this down a little bit, maybe, so it's more visible. And then in the attributes, I'm just reversing the velocity that it's inheriting from the source points and cutting it in half. Everything else is default.
Okay, great. Thank you.
All right, next steps, and this is going to mimic the build that we'll do tomorrow in a much more real-time environment. So
and where did you get the velocity from?
So the velocity is when we calculated the direction here in our growth solver. We calculated the direction by subtracting the current point from its neighbor. And then that's being output into this vector attribute called dir. And then actually, that's true. I'm not sure if I went over this. Downstream from the solver, we're saying v at v, the velocity is equal to the normalized direction attribute. And that just makes it 0 to 1. All those vectors become 0 to 1.
Very cool.
Easier to manage. And yes, and we can visualize that here pretty easily. See them. So, all right. So next, let's set up some quick pyro. So pyro source. And we want to initialize source smoke. We're not going to use temperature, so let's get rid of that. And the only reason we need density really is so we can visualize it, because the only thing we're getting from the pyro is velocities. Next, we need a rasterize, volume rasterize attributes. I can't seem to type today, I'm sorry. Volume rasterize attributes takes the values that are being created here by the pyro source and turns them into volumes that can be used to source pyro. So the attributes that we need are density and velocity. Now, so let's maybe drop that in half or even less. So here we have our volume source. And then next, put in a pyro solver, our second solver of solver madness. Although technically pop nets are solvers too, so third solver. And I'm going to leave everything at default for the moment and just cut the resolution in half, or maybe, yeah, in half, and just run this. And again, you can see that the velocity that we're sourcing is pushing it all downward. I don't have any temperature on this. So I think you can guess where this is going. We can go here to the sourcing. And first of all, we don't need a source temperature at the moment, and we can get rid of flame. And let's invert the velocity again, and this time double it. And what that'll give us is it'll push it upward. So if we visualize this. So now we're sourcing pyro from the same points, and they'll match up. It'll match up perfectly with the geometry that we're getting rid of. And that density is great to visualize, but we don't really need it. What we're going to do is we're going to take the output from the pyro solver, put it into the second input of the PopNet. Dive inside here and use pop advect by volumes. And like we talked about earlier, advect is we're just adding the velocity vectors to the current velocity of these points from the pyro. So second context geometry, and let's update the velocity in this case. And we're going to just blend that to 0.5. So take half of, blend it by half. And then let's take a look. And this is going to be pretty quick because we don't have a lot going on. And then we have, now we're getting kind of that bubbly motion that we needed, the sort of swirling. You can see it's getting those velocities from the pyro to give us much more of a watery effect. And as you can see here, since we're updating velocity, they're all kind of coming to a stop, and that's fine. We can layer some other things on top of that. In fact, one of the things that's happening is as the pyro dissipates, we're not able to get velocity from it anymore. And we can change that pretty easily by going to our fields and turning down the dissipation maybe to 0.01. So yeah, so it gives us much more visual interest. And I would encourage everyone to play with this with other geometry, play with those settings to see what the outcomes are, because it's very versatile. And then, yeah, any changes we then do with the pyro here, like for instance, it might add a little more visual interest maybe by adding a little bit of turbulence. Size is probably too large. Let's give it 1. And that'll add that turbulence into onto our points and give us some more interest. Any questions at this stage?
We do have a question. Why not use buoyancy instead of inverting velocity into the pyro solver to make it go upward?
I actually did. I was actually using buoyancy I was actually grabbing a lot of attributes off of the pyro with this volume attribute. What is it? Pop attribute from volume. You can get all kinds of attributes like that. I was actually at one point using temperature to adjust the scale of particles, and that's totally doable. This is a very straightforward way of doing it to me,
Yeah.
but it's up to you. You could totally do it that way. Anything else?
I think that's it, but sometimes questions come right after we finish asking. There's questions. No, I think we're good. I think we're good. Yeah.
Okay. All right. So yeah. So what we have here is in a very simple form, we basically have the building blocks for our bubble-ize effect. Essentially, everything else that we're going to do from here on is just layering on different sourcing for this. We're going to use this same ramp here to source flip and to source multiple particle systems. And then we're going to add rules to those particles to do other things once they spawn. I think that's it for the solver. let me make sure I've covered everything, because then we can move on to caching, cache management, and PDG, and building control panels. I think we're good, right?
I think we're good.
Okay.
Yeah, so Philip is saying super fast after the time shift. That's a vital step. I think that is a vital part of your demo today, right?
The things that are happening after the time shift here.
Yeah, like the fact that you can retime it after the caching.
Yeah, that's a critical part of this effect, is that
Yeah.
we can run the solver, we can run this growth solver however many frames we want. And then after that, it's all keyframes, just by animating these ramps, setting width. Does that make sense?
Totally, and that's what optimizes it. It's great. Thank you.
Yeah. In fact, what I would do, and this is probably how it's set up, is we want to link these attributes. So this is our source ramp, and this would be our object ramp. And then we can take copy parameter, take this and make sure this is linked. Paste relative reference. And same for the width. Yeah. Okay. Well, let's talk about some housekeeping. A critical part of this whole process when you're dealing with a lot of different simulations and layering them all together is just management. How do you not get lost? Build an effect that and I've done it with myself plenty of times, build an effect that's you can get lost in not knowing what's going on, and it's hard to troubleshoot or manage. A big part of that is going to be how you build out your caching and building control panels. So let's talk about this real quickly here. One of the first things I always do when I'm building an effect is create a control panel that at least has the frame range you're working with. So drop down on null. And if you go here to the shape palette, I usually like to use a circle just to differentiate. And then here we can just add as many attributes or as many parameters as we want that we can link later on. And you'll see in the next session, I have actually a ton of controls here in the main effect build. In this control here, we have a bunch of different tabs that can gather all the main parameters into one area. And this is really critical. You want to be able to control your caching, your frame ranges, and all the primary parameters for your sims in one area. Otherwise, you're going to be diving into, different solvers, different .NETs, and it can become a little confusing after a while. So the way we're going to do that, I already have one here, but let's go ahead and build one. Call this control. If only to have a frame range. So what I've gone here and I've opened edit parameters interface, and we can actually make these invisible by checking this. And then we'll drag over a vector 2. We'll call this range. So that's the name of the parameter, and then the label is what we'll see on the parameter. In our case, we're going from 2001 to 1150. And this is because a lot of times you're going to be changing your frame range here. We don't want to be referencing f-start and f-end. We want these to always stay the same. So you can, once you have that, copy parameter, and then that really needs to be pasted into every solver as the start frame. I'm already doing that here. And that's also going to be referenced for caching. So that does bring us to caching. and cache management in PDG. Now, I'm going to go over a few things that work really well for me that I've used on commercial projects for years. And this is a personal opinion kind of situation. I like to use what I call a deconstructed file cache. So rather than using a file cache node, which is great, but it makes a lot of assumptions for you, and it has a lot of things, a lot of attributes that I don't want to really be interacting with in the file cache node. I want everything, I want to gather everything here into this PDG network. I want all the main cache attributes to be here, not spread all over my HIP file. If that makes sense. So the file cache defaults to HIP name too. And even though you can change that to something else, it's really sometimes hard to keep track of where your caches might come from. So if I run this, for instance, if I run this file cache, it will harden this name. In other words, it won't be a file token anymore that says HIP name. In fact, I'll just save one frame.